This video is going to cover angle of twist. Angle of twist is another really easy equation, and it has like a little sing-songy kind of tune to it. It's phi is equal to T times L over J times G. Very similar to the axial deformation one, but just with incredibly different variables. So let's begin. Phi is obviously angle of twist. That's this guy. And his units are radians. Even though he is an angle, we are doing angles in radians. Next up, we do have T. T is torque. We all know and love him. Torque is either going to be in pound inches or Newton millimeters. I do recommend, though, even though you're never going to be given pound inches or Newton millimeters, that you do convert your unit of length in there, be it feet or meters, down to a smaller unit, the inches or millimeters. And same thing goes for the length. That's coming up next. Length here, L, you want it to be either in inches or millimeters, because otherwise your units aren't going to cancel with downstairs, J and G. Now we've already seen J and we've already seen G before. J is the polar moment of inertia. That's going to be in inches to the fourth or millimeters to the fourth. And G is going to be the modulus of rigidity, and the modulus of rigidity is either going to be in KSI, but we don't really want to do kips if the upstairs in pounds, so we'll say PSI, it's a pressure, or currently our units are Newton per millimeter squared, and this is a megapascal. So again, usually G is going to be given in gigapascals, and again, a gigapascal is just simply 10 to the third megapascals. So just be really careful when you're doing stuff with angle of twist that you're really paying attention to your units, because if you don't pay attention to your units, you're not going to get an answer that makes any sense whatsoever. So now we're going to do an example, and this example is quite different from pretty much anything that you've probably normally seen in regards to angle of twist. Here we have a nice, we have a fixed end over on this side, and there's some solid going on into here until it hits A. So A here is a solid surface. This is just a very solid rounded surface here that connects from the fixed end to A. So A is solid, but then what's coming out of A is two things. We have the tube, and the tube here is going to be having a moment, or a torque in this case, because it's a twisting moment, and that twisting moment is 21 kilonewton meters. So again, that's the tube that's there on A. Forgot that little bit right there as well. So that's the tube. So that tube's going to cause twisting at A, but then there's yet another thing, and that is a solid rod that comes straight out of A all the way over here to C. So there's that thing as well that's acting on it. So hopefully with the highlighter there, it makes a little bit more sense. We have a tube and a pipe both acting at A. So at B, the end of our tube, we're twisting one way, and at C, the end of our pipe, or the end of our bar, we're twisting the other. So we're going to have the same material for both of these. We're going to say that our modulus of rigidity is 75 gigapascals, but the outside diameter of AB is 60 millimeters, and it has a wall thickness of 5 millimeters. And the diameter of bar from A to C, because it does all the way go back to A, that's going to be 30 millimeters. And what we want to find is the angle of twist at A that's being caused by these two loads. So again, our equation for angle of twist, phi, is equal to T times L over J times G. Right, so J, again, polar moment of inertia, is based on the cross-section, and we're going to start with AB first. So we want to find the angle of twist at AB. Again, we're going to need to know what J is for AB, and that's going to be pi over 2 times the outside radius to the fourth, and the radius would be the diameter of 60 millimeters, divided by 2, raise that to the fourth, minus the inside radius. Now the inside radius is going to be the outside of 60 millimeters, divided by 2. That's the outside radius now. However, Now we're going to minus off our thickness of 5 millimeters. That to the 4th, and that is J. So we're going to get that J for section AB here is going to be 6.58 times 10 to the 5th, actually, millimeters to the 4th. Now wall thickness was pretty skinny. So there we go, 6.58 times 10 to the 5th millimeters to the 4th for J. G is given, L is given. L is going to be that 1 meter, and T is given. So now we can actually solve for the angle of twist at A caused by B. So again, we have T. T is our applied load. Our applied load here is 21 kilonewton meters. Now you can see they're going in different directions, so perhaps it's really good to figure out which one of these is positive and which one is negative. And we're going to do that using right-hand rule. Remember, we're going to make a cut over here at A, and we're going to see which way it twists about our thumb. That would be sticking outward. If our thumb sticks outward, then technically that direction, going back behind here, would be the positive direction using right-hand rule. But that's also in the direction of our load, so technically we're going to be getting a negative 21 here. So this is minus 21 kilonewton meters, and we have a length. Our length there is 1 whole meter. Right, our length from A to B is 1 whole meter. Fantastic, right? But nobody likes meters, right? We very much said we need to not have meters, so we're going to have 1,000 millimeters in 1 meter, and we're going to square that, and that'll take care of 1 thing of meters and 2 things of meters. So yay, so then all over J will leave in red because he had to do with our diameter here. So that's 6.58 times 10 to the 5th millimeters to the 4th. Then times G, and G we had up here in orange was 75 gigapascals. So remember that a gigapascal is a kilonewton per millimeter squared. So now we've got millimeters here, we've got millimeters here, millimeters, 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 and we've also got kilonewtons and kilonewtons. So thankfully everything's going to cancel out, and that's going to leave us with radians, but very specifically negative because we had a negative twisting. And believe it or not, this isn't really very big. This is 0.426 radians. Yeah, actually really small. If you think about it, it's really not that big. So now let's do it for C, but again for C it's actually from A to C because again he does start at surface A. So his torque, his direction here, we'll just kind of erase the ones that we got going on back there. This time when we're going to make our cut to see if he's positive or negative, still cut is at A. Still we're looking outward, thumb in the outward direction, and again we would be going that way around for positive, which is exactly opposite of C. So yes, this one is going to be positive. So this time our force is positive 5 kilonewton meters. Our length we have from A to C is 4 meters, right? So times 4 meters, but again nobody likes meters, so 1,000 millimeters per 1 meter. Yep, squared. And then all over J. What is J? But this is a solid one. We didn't solve it ahead of time, but it's solid where his diameter is 30. Okay, so J for a solid is pi over 2 times the radius to the 4th. Well, the radius is going to be 30 millimeters divided by 2. Since 30 is the diameter, divided by 2, raise it to the 4th. That is going to be J. So that's going to be millimeters to the 4th, and then lastly times G, and G we have as 75 gigapascals, which is a kilonewton per millimeter squared. So again, we've got our, let's do different color here, millimeters canceling, here our meters all canceling, so now we've got millimeters and millimeters and millimeters, everybody's in millimeters, and we still do have kilonewtons and kilonewtons. So everything we're going to get is going to be in radians. And again, this one's positive, so we get a positive 3.35 radians. So if I want to find the actual total angle of twist at A caused by those loads, I'm looking at the AB rotation, which is minus 0.426, and then the AC rotation of plus 3.35 radians, and I'm going to get a grand total of positive 3.10 radians. So ta-da! So again, when you're looking at angle of twist, definitely do take into account the actual length of the member, not just how much further it is, especially when you have this weird little situation of a solid inside of a hollow. So hopefully you find angle of twist not too bad, because it's not really too terrible.